Hey everyone, welcome back. I'm Darshan, and this is part 3, the final episode of our Rust WAF series. We've been on a wild ride. In part 1, we built the foundation, architecture, dependencies, project structure, the core design. In part 2, we went deep on security, SQL injection, XSS, path traversal, command injection, rate limiting, IP filtering, bot detection. Today, we make it real. We're deploying this thing, setting up monitoring, running benchmarks, watching it block attacks in real time, and covering everything you need to run this in production. By the end of this video, you'll have a fully deployed, monitored, and battle-tested WAF protecting your applications. Let's finish this. Here's the plan for today. First, we'll build and run the WAF locally with the mock backend. Then we'll fire attack payloads at it and watch them get blocked. Next, we'll look at Prometheus metrics and how to visualize them in Grafana. After that, performance benchmarking with REQH. Then Docker deployment, Kubernetes setup, and finally, production best practices and hardening tips. A lot to cover. Let's move fast. The build process is straightforward. You clone the repo and run the release build command through cargo. The release flag is important. It enables full optimizations, link time optimization, single code gen unit, and optimization level free. These are configured in the cargo.toml under the release profile. The debug build works for development, but you lose about 40% of throughput compared to release mode. For benchmarking and production, always use release. The initial build takes a few minutes because we're compiling Pingora and all its dependencies. Subsequent builds are much faster thanks to Rust's incremental compilation. Before starting the WAF, we need something behind it, a backend server for the WAF to proxy to. The project includes a mock backend example built with Tokyo. It's a simple HTTP server that listens on port 8080 and responds with a basic message for any request. Run it in the background. It'll print a message confirming it's listening. This simulates your real application. In production, this would be your API server, your web app, whatever you're protecting. Now start the WAF itself. When it launches, you'll see a nice startup banner in your terminal. It shows the WAF proxy address on port 6188, the metrics endpoint on port 6190, the upstream backend address, the config file being used, and the running status. That's it. The WAF is now intercepting all traffic on port 6188 and forwarding clean requests to the backend on port 8080. The command line interface gives you several options. The config flag lets you specify which config file to use. The upstream host and port flags let you point to any backend. The listen address and port control where the WAF listens. The metrics port configures the Prometheus endpoint, and the testing mode flag, which loads a relaxed config for development. You can mix and match. Point to a remote backend, use a custom config, change ports. Everything is configurable without touching the source code. Let me show you what happens with normal traffic first. Send a GAT request to the WAF on port 6188 to the path API/test. You'll get a 200 OK response with the body from the mock backend. The request passed through all security checks, was forwarded to the backend, and the response came back. That's the happy path. Transparent proxying. The client doesn't even know the WAF is there. Now, let's try some attacks. Send a request with a SQL injection payload in the query string, something like ID equals 1 single quote space OR space single quote space OR space single quote 1 single quote equals single quote 1, boom, 403, forbidden. The WAF caught the Boolean injection pattern and blocked the request. In the WAF logs, you'll see a warning message, SQL injection detected in URI, with the full payload printed. Let me try a more sophisticated one. A union select attack. Send Q equals 1 single quote space union space swake 4 space sign space from space prom space passwords double dash 403 again. Union-based injection detected. How about statement termination? I equals 1 semicolon space drop space table space users. Blocked. The semicolon followed by a destructive SQL command was caught. Every single attack attempt returns a 403 and logs the violation. 0 got through. Now cross-site scripting. Send a request with a script tag in the query parameter. The WAF catches the script tag pattern and responds with 403. Try an image tag with an on-error event handler. Blocked. Event handler detected. Try a JavaScript protocol and a parameter. Blocked. The XSS detector is catching everything we throw at it, both in URL parameters and in request bodies. If you send a post request with XSS in the JSON body, it catches that too. For path traversal, send a request with .. sequences in the path. Something like /API/files/././SSA/pass wall. Blocked. Directory traversal detected. Try encoded variants. Replace the dots and slashes with their %encoded equivalents. Still blocked. The detector decodes before checking. Try accessing .git/config directly. Blocked. Sensitive file access detected. Command injection. Send a request with a semicolon and a shell command, like host equals google.com rmzc sexthds sexhrft sal operator followed by dangerous command. Try a pipe, localhost pipe cat space /etc/have to /passwest. Blocked. Pipeline with sensitive file access. Backtick injection. Query equals backtick huami backtick. Blocked. Rate limiting is fun to demo. Send a bunch of requests rapidly in a loop. The first 100 go through with 200 OK. Request number 101, 429, too many requests. The rate limiter kicked in. Wait 60 seconds for the window to reset, and you can send again. The per IP tracking means different IPs get independent rate limits. For bot detection, send a request with a user agent that matches a known attack tool. Set the user agent to SQL map. 403. Blocked bot detected. Try Nikto. Blocked. Try a random scraper pattern. Blocked. Now send a request with Googlebot in the user agent. 200. OK. The good bot allow list lets legitimate crawlers through. Try sending a request with a content length header that exceeds the max body size. Set it to 10 million. 413. Payload too large. The WAF rejects it before even reading the body. The project includes a comprehensive security test suite as a Rust example. It automatically runs all these attacks and more, and reports results. Fire it up and watch it go. It tests legitimate requests first, confirming they pass. Then it hammers the WAF with SQL injection variants, XSS payloads, path traversal attempts, command injection, rate limiting, and oversized bodies. At the end, you'll see the test summary. Total tests, passed veiled, success rate. You should see 100% pass rate, all attacks blocked, all legitimate traffic allowed. This test suite is your safety net. Run it after every code change. Run it after every code change. If all tests pass, your WAF is working correctly. Every WAF needs observability. You need to know what's happening. How many requests are coming in? How many are being blocked? What types of attacks are hitting you? Our WAF exposes Prometheus metrics on port 6190 on the metrics endpoint. Hit that endpoint with a GAT request and you'll see raw Prometheus metrics. The three main metrics are WAF WTAG, TOTRFL WASTs, a counter of all requests received. WAF, hour, Waller, WP requests, a counter of requests that passed all checks. And WAF WTAG, .FL walked, requests, with a reason label, counting blocked requests by attack type. The reason labels include SQL unchecked, XS URI, XS US body, rate SQL emit, IP bell listed, bot duscaro, DP detected, body uscaro large, path uscaro large, path large carolo, and command uscaro injection. You get granular visibility into exactly what your WAF is doing. These are atomic counters, no locking, no performance impact. They increment on every request without affecting throughput. To scrape these metrics continuously, you set up Prometheus to poll the WAF's metrics endpoint. The project includes a Prometheus alerts.iml file with pre-built alert rules. You configure Prometheus to scrape the WAF every 15 seconds. It stores the time series data and provides query capabilities through PromQL. Some useful queries. Rate of total requests over 5 minutes. Rate of blocked requests by reason. Percentage of allowed requests. Block rate spike detection. For visualization, we use Grafana. The project includes a Grafana dashboard JSON file that you can import directly. The dashboard shows 4 panels. Total request rate over time. Blocked versus allowed requests. Block distribution by attack type as a pie chart, and a timeline showing when each type of attack was detected. This is your WAF command center. At 2 a.m. when someone's attacking your site, you pull up this dashboard and instantly see what's happening. Are you seeing a spike in SQL injection attempts from a specific IP range? Block the range. Are XSS attempts increasing on a specific endpoint? Investigate the application code. The dashboard makes the invisible visible. Without it, attacks could be happening silently and you'd have no idea. The Prometheus alerts.imo file includes pre-configured alert rules for common scenarios. High block rate alert fires when more than 50% of requests are being blocked over a 5-minute window. This could indicate an active attack or a misconfigured WAF rule that's causing false positives. WAF down alert fires when the metrics endpoint stops responding. Your WAF is offline. Rate limit surge alert fires when rate limiting blocks spike, indicating a potential DDoS or brute force attack. These alerts can integrate with PagerDuty, Slack, email, or any notification system Prometheus supports. Let's talk performance. Claims are nothing without benchmarks. We use REK, a modern HTTP benchmarking tool, to measure real throughput and latency. The benchmark setup: use the benchmark config which disables rate limiting so it doesn't interfere with throughput measurement. Start the WAF with the benchmark config, then run RK with 10 threads, 100 concurrent connections for 30 seconds. Here are the actual results from running on standard hardware. 15,143 requests per second. That's our throughput. 6.6 millisecond average latency. 42.7 millisecond maximum latency, 100% success rate, 0 errors. Over the 30-second test, 455,000 requests processed. Nearly 500,000 requests without a single error. That's stability. Let me put these numbers in context. Mod security, the industry standard WAF for Nginx, typically handles around 5,000 requests per second with 15 to 30 millisecond latency. Our WAF is 3 times faster with half the latency. ASWAF, the managed service, handles about 10,000 requests per second with 8 to 12 millisecond latency. We're 50% faster. Cloudflare's Edge WAF handles 50,000 plus requests per second, but that's running on their global infrastructure at the edge. Apples to oranges. For a self-hosted WAF running on a single instance, 15,000 requests per second is exceptional. And this is for a single instance. Horizontal scaling is straightforward. Run multiple WAF instances behind a load balancer. Each instance handles 15,000 requests per second independently. 2 instances, 30,000. 4 instances, 60,000. Linear scaling because the shared state is minimal. Rate limiting state isn't shared across instances, which means per IP limits are applied per instance. For most deployments, this is fine. For globally distributed setups, you'd use a centralized rate limit store like Redis. Memory usage is around 100 megabytes under full load. That's remarkably lean. The compiled regex patterns take about 80 kilobytes. The dash map grows with the number of unique IPs being tracked. The body buffers are capped at 1 megabyte each and cleared after use. Compare that to mod security, which typically uses 300 to 500 megabytes, or Java-based WAFs that eat a gigabyte of RAM just for the JVM. Rust's zero-cost abstractions and lack of garbage collection pay dividends here. No GC pauses, no memory bloat. Predictable performance under load. For Docker, the setup is clean. We use a multi-stage build. The first stage uses the official Rust image to compile the release binary. The second stage uses Debian Slim, copies the binary and config files, and sets the entry point. The result is a container that's about 80 megabytes. Small, secure, and fast to deploy. Run the container, mapping ports 618 and 6190. Mount your configuration directory if you want custom configs. Done. Docker Compose is even simpler. Define the WAF service, the backend service, and optionally, Prometheus and Grafana services. One command brings up the entire stack. You can even scale WAF instances with Docker Compose. Scale the WAF service to 3 replicas and put a load balancer in front. For Kubernetes, the project includes deployment manifests. A deployment with configurable replicas, resource limits, health checks, and a config map for the WAF configuration. The liveness probe hits the metrics endpoint. If it stops responding, Kubernetes restarts the pod. The readiness probe does the same, ensuring traffic only routes to healthy pods. Resource limits are set conservatively, 100 millicores CPU and 128 megabytes memory for requests, 500 millicores and 256 megabytes for limits. Adjust based on your traffic patterns. A service exposes the WAF internally and an ingress or node port exposes it externally. Pretty standard Kubernetes patterns. The config map holds the WAF configuration YAML. You can update it and trigger a rolling restart to apply new rules. For bare metal or VM deployments, systemd is the way to go. The project includes a service unit file. It sets the working directory, the startup command, environment variables, restart policy, and resource limits. Enable it, start it, and it runs as a background service that automatically restarts on failure. Check status with systemctl, view logs with journalctl. This is the simplest deployment option, no containers, no orchestration. Just a binary and a config file. I mentioned hot reload in part 1, and here's where it pays off. In production, you don't want to restart the WAF to change rules. Every restart means a brief window where traffic isn't protected. With hot reload, you edit the config file, save it, and the WAF picks up the changes within seconds. The file watcher using the notify crate detects the modification event, loads the new config, validates it, and swaps it atomically. Current in-flight requests continue with the old config. New requests use the updated config. No dropped connections, no downtime, no gap in protection. You can even script this. Detect a new attack pattern, append a rule to the config file, and the WAF starts blocking it immediately. Automated incident response. Let me give you a production readiness checklist. Number 1, always run the release build. Debug builds are significantly slower. Number 2, use the production config. It has stricter rate limits, enabled IP filtering with your internal networks whitelisted, and all security modules in block mode. Number 3, setup monitoring. Prometheus plus Grafana is the minimum. You need to see what's happening in real time. Number 4, configure alerts. High block rates, WAF downtime, rate limit surges. You should get notified automatically. Number 5, run the security test suite regularly. After every code change, after every config change, after every deployment, automated testing is your safety net. Number 6, log everything. Set the log level to info in production. Keep the logs for incident forensics. Use structured logging so you can grep and filter efficiently. Number 7, keep the WAF updated. Security is a moving target. New attack patterns emerge constantly. Update your regex patterns. Update your bot detection lists. Stay current. Number 8, test in log-only mode first. When you add new rules, run them in log-only mode for a week. Check for false positives. Once you're confident, switch to block mode. This prevents breaking legitimate traffic with overly aggressive rules. A few things to watch out for. Don't put the WAF behind a CDN that strips X-forwarded for headers. The WAF needs the real client IP for rate limiting and IP filtering. Don't set the max body size too low for file upload endpoints. If your app accepts 5 megabyte uploads, set it to at least 6 megabytes. Don't forget to allow health check paths. If your load balancer probes/health, make sure the WAF allows it through without security checks. Don't ignore the metrics. If you see a sudden spike in blocked requests, investigate. It could be an attack. It could also be a false positive blocking real users. And that wraps up the entire series. Let's look at what we built across all 3 parts. Part 1, the architecture. Pingora framework, project structure, dependencies, the security rule trait, the WAF proxy, thread safety with ARC and DashMap, and YAML configuration with hot reload. Part 2, the security modules. SQL injection with 15 patterns. XSS with 10 plus patterns, path traversal, command injection, rate limiting with sliding windows, IP filtering with CIDR, bot detection, body inspection with 2-stage size checks. Part 3, production readiness. Building and running the WAF, live attack demos, Prometheus metrics and Grafana dashboards, performance benchmarking showing 15,000 requests per second. Docker, Kubernetes, and systemd deployment, hot configuration reload. Production best practices. This is a complete, production-ready WAF. 2,500 lines of Rust. Battle-tested patterns. Real-world performance. The project is open source and actively maintained. Here are some features on the roadmap. GeoIP blocking. Block traffic from specific countries. WebSocket support. Inspect WebSocket frames, not just HTTP. Machine learning-based anomaly detection. Go beyond regex patterns. Response body inspection. Currently we only inspect requests. Distributed rate limiting with Redis for multi-instance deployments. If any of these interest you, check the GitHub issues. Contributions are welcome. This series took a lot of work. If it helped you, here's what I need from you. Subscribe to the channel. I'm building more Rust and security content, multi-agent systems, production deployment guides, more frameworks. Star the GitHub repo. It helps others discover the project. The link is rmdev/hub/Pingora WAF. Join the Discord community. That's where we discuss code, debug issues, and share projects. The link is in the description. Support the work. Buy me a coffee if this series saved you time or taught you something new. Every contribution funds more tutorials like this. Drop a comment telling me what you want to see next. More Rust? More security? More DevOps? Let me know. This has been an incredible series to make. Building a production WAF is one of the most rewarding projects in systems programming. It touches everything: networking, security, concurrency, performance, monitoring, deployment. I hope this series gave you the confidence to build your own infrastructure tools in Rust. Don't just use tools. Understand how they work. Build your own. That's how you grow as an engineer. Thanks for sticking with me through all 3 parts. I'm Darshan. Keep building, keep learning. And I'll see you in the next one. Peace.